Thank you very much for the introduction. Good morning, ladies and gentlemen. I want to give you this morning an introduction into the topic large to very large tunnel boring machine diameters for the construction of today's infrastructure projects. The motivation for large to very large tunnel boring machine diameters goes back to the demand of increasing the capacity for infrastructure projects. This was main focus on road tunnel jobs, where there's the demand generally over in Europe to go from 2-lane road tunnels to 3-lane road tunnels, or for example, for combined usage of the tunnel profile to integrate in the tunnel profile road traffic and rail traffic, or for a project that was realized in Malaysia and Kuala Lumpur for the stormwater and road tunnel project, where you have also, in case of floodwaters, the possibility to drain water through a tunnel that also combines road traffic. If you look back over the last 35 years, you see that there was a great trend towards going for larger diameters. In the early 80s, a nearly 6-meter diameter machine was built for a project over in Germany. Then in 1996, very large diameter at that time had been in the range of 10 to 12 meters. But then in 97, there was the first project with a very large diameter at that time, with a diameter of 14.2 meters. That was for a road tunnel job over in Germany, in Hamburg, for 2-lane road tunnel. If you look then towards the past, in 2006, there was for the M30 in Madrid, it was a highway tunnel project through the city center of Madrid, was already a very large diameter with a diameter of 15.2 meters. And if we look now today, the largest machine that successfully finished excavation has a diameter of 17.6 meters that was applied for a highway tunnel job in Hong Kong in China. I will address that project later on. There's already a concept design existing for even diameters in the range of 19.5 meters in diameter. Looking for very large diameter projects, I want to give you some references of mix shields and how the development came towards larger diameters, exceeding the diameter of 15 meters. If you look to the first project listed here, the Westerschelde Tunnel project, that's a road tunnel that was realized in the Netherlands. At that time, two 11.34 meter diameter mix shields were used to excavate each section of 6.6 kilometers. But here not only the large diameter was a demand for tunneling, it was also the demand to go through sticky clay conditions, glauconitic sands, which are abrasive sands, but also this associated with very high hydrostatic pressures in the range of 7.5 bar. Then a project that was realized in Shanghai in China. Here we supplied two mix shields with a diameter of 15.4 meters that connected the mainland of Pudong in Shanghai towards an island that called Changqing Island. Here the mechanized solution was the only possibility because you have here in Shanghai the harbor entrance, and so an immersed tunnel tube construction method was not feasible because you have to keep the shipping lane free for ship traffic. These two mix shields each excavated a section of 7.2 kilometers in clay formation with shell debris and also with high hydrostatic pressures in the range of 6 to 7 bars. If we talk now about large diameter earth pressure balance shields, that's another type of soft ground tunnel boring machine. The first big step was with the design and manufacturing of the machine for Madrid for the M30 project. That's the inner road tunnel job in Madrid in Spain. The machine with 15.2 meters was at that time the largest diameter for an earth pressure balanced shield, and the demand was to excavate in urban area with underpassing of partially quite sensitive infrastructure project. The tunnel had a section of about 3.6 kilometers that could be excavated within 8.5 months, and the machine performed quite well and finished its job about 4.5 months earlier than actually scheduled. Another big EPB application was for a job in Italy, also a highway tunnel job carrying 3 lanes of traffic in the tunnel profile. That machine had a diameter of 15.6 meters, and it had to excavate 2 parallel tunnel sections of 2.5 kilometers. But here, not only the diameter of 15.6 was a demand, it was also the geology that was characterized by clay formation, claystone, mudstone formation. But what was a special demand was that along the entire 2.5 kilometer long section, there was a presence of methane gas that demanded to operate that machine along its entire route in a closed earth pressure balanced mode. But I want to concentrate on 2 specific demanding projects that had been realized. The first project is the Bosporus crossing in Turkey, in Istanbul. Here we supplied a large diameter earth pressure mixed shield that had a diameter of 13.7 meters. It's the first road tunnel that connects the Asian side of Istanbul in Turkey with the European side. The tunnel has an overall length of 3.34 kilometers, and it's for a total of 4-lane road tunnel, 2 lanes of traffic on each deck. The demand here was also not only the big diameter, but this in association with quite complex geological formations with locally full face in rock that comprised sandstone, mudstone formation, full face of soft ground, and also mixed face conditions. But another demand was the tunnel was about 100 meters beneath the sea level. So the machine had to be designed for a pressure of 13 bar. And you see on the next slide the geological cross-section. From the right-hand side, the machine started tunneling. That's from the Asian side, already tunneling for the first 100 meters in full face rock conditions. Then a transition zone rock soft soil, and at the deepest point of the tunnel, where you had 100 meters of sea level above the tunnel crown, you had been excavating in soft soil. And then going back into transition zone, soil mixed phase condition, and full phase rock condition. The demand here was for safe tunneling into these demanding conditions. That's why we supplied a mix shield of 13.7 meters in diameter. The cutting wheel was specially addressed to the predicted geological conditions. The cutting wheel was fitted with 19-inch disc cutters and soft ground tools, strong wear protection because of the abrasive nature of the predicted rock mass. And what was specific in case, because of the high hydrostatic pressures of 13 bar, was that the 6 main arms of this cutting wheel had been designed accessible in atmospheric conditions to change all the tools that are on the red main spokes of the cutting wheel could be safely changed backwards under atmospheric conditions. To also support or monitor possible wear on the cutting wheel structure, the cutter head was fitted also with sectorized wear detection loops that gave an additional safety in respect also of maintenance and control of the cutting wheel. Here you see a cross-section into one of the 6 main spokes where personnel can enter in atmospheric conditions. The middle picture shows the actual procedure of the tool change. You see here some water involved. That's not coming from the front. That is just to use for cleaning for the housing. And the right picture shows you the cutter housing and for the soft ground tool housing in the specific atmospheric arms. Here you see the possibility of non-exposure maintenance for the tool change. You see the retraction of the center of a disc cutter, then closing of a gate, and this closing of the gate and the possibility to retract then the disc cutter to the backwards. It keeps the front completely sealed off from earth or from water pressure, thus that you are able to change here safely backwards the disc cutters in atmospheric conditions. Here you see some other illustrations of tool change. It looks like the people have enough space, but actually the picture was taken with a wide angle lens. So actually you have a quite narrow space where the workers here can do the tool change. Another feature of the tunnel boring machine was that each of the 19-inch disc cutters were equipped with a disc cutter rotation monitoring system. That disc cutter rotation monitoring system measures if the disc cutter is rotating and also measures the temperature of the tools. And this exactly is an advanced tool to steer the process of cutter tool change. You don't have to enter in the chamber because you think that the tools are worn, but you get the indication in the operator's cabin, and the picture on the right is exactly what the TBM operator sees in his control cabin. He has that picture on his monitor. The green circles that you see, these are the disc cutter tracks, and in the center you see a red circle, that's the center disc cutter. It shows that the center disc cutter is blocked, that it's not rotating. The yellow circles here give a critical value, so that the disc cutter is sometimes rotating, sometimes not, and that gives you the indication that you have to enter into the chamber to exchange these 3 disc cutters on the track, on the cutting wheel track, and to avoid further damages on disc cutters or even on the cutting wheel structure. But nevertheless, the security for the TBM to be applied to 13 bars of pressure, and also the devices such as accessible disc cutter cutting wheel arms does not give you a 100% guarantee. You always have to design your TBM with a redundant system in case that you have an unforeseen failure, that you have to be able to send in people even under quite high pressures of 6 bar, 8 bar, or even 13 bar if there's a need to. So that's why right from the beginning, when you design your tunnel boring machine, you have to design that the people can enter under saturation for tool change or even for maintenance and repair work. And if we talk then about works under hyperbaric or saturation conditions, you have to have also a habitat on surface where you have to adjust the divers to the high pressures. Then they are sent down to the machine in a kind of transfer shuttle that you see on the picture in the middle. This crew shuttle was brought down to the machine with a multi-service vehicle. Then it's more an automatic process. There's a hydraulic lift at the backup system to the middle deck, where you have then the motorized shuttle towards the front to the shield area, where you have another lifting table to lift that crew shuttle that can dock then to the permanent installed airlock, thus that the divers could enter in the chamber under saturation if there would have been a demand to do so. That picture here gives you an overview about the actually faced support pressures. From the right-hand side on, that was the start of the tunnel boring machine. On the Asian side, you see that along the majority of the alignment, the pressures had been well above 3.5 bar, which is the actual limit for compressed air works, where you can send in normal people. But everything that is exceeding pressures of 3.5 bar, you have to send special trained people or divers in for maintenance or repair work. So the actual maximum phase pressure had been in the range of 11 bar, and along the majority, more well above 8 bar of support pressures. The 3.3 kilometer tunnel were excavated with an average performance of 7 meters per day. And finally, the lessons that we learned for this tunnel operation under quite complex conditions was that here these accessible cutting wheel arm and also this cutter rotation monitoring system showed had been one of the major tools to lead for the success of the TBM operation. And what is always important for such complex conditions, that you have a very good partnership already from the early design stage with the owners, with the planners, and also with involvement of the machine manufacturers. The tunnel in Istanbul was opened for traffic in December last year, and is frequently taken into operation. The next big project I want to address to is the application of the up-to-date world largest tunnel boring machine. The machine you see here, it was assembled in our factory. It has a diameter of 17.6 meters. On the left-hand side, you see a smaller machine. That's not a micro-tunneling machine. That's a 6-meter earth pressure balance shield. So you see the big diameter differences towards the 17.6-meter machine. The machine is a mix shield. It was applied to the Tuen Mun Chek Lap Kok Link in Hong Kong. That's an overall section of 5.5 kilometers of highway, of which 2 parallel tunnels of 4.2 kilometers were built using 2.5 machines. One section of the bored tunnel comprised a section of 650 meters where the 17.6 meter machine was in use, and the remaining tunneling section was finished with 2 14-meter mix shields. The geology for that project was also quite demanding, about 50% in alluvial soils, 50% in mixed phase alluvial soils, and fresh granite with high unconfined compressive strengths of up to 250, 280 megapascal. You see here the breakthrough of the machine after 650 meters. For one section, the 17.6 meter machine operated. The same machine then was, the diameter was decreased from 17.6 to 14 meters to finish the remaining tunneling section. And on the parallel lot, it was foreseen to excavate it along its entire length with a 14-meter diameter mix shield. You see here the diameter decrease from 17.6 to 14 meters. All the backup equipment was used one-to-one. The same center drive was used, the center cutting wheel for the adaptation towards the 14-meter diameter. The outer elements of the cutting wheel were attached to the 14-meter diameter. And then the same machine finished the excavation of the 4.2 kilometers. You see the picture on the upper right. The machine started in the starting shaft for the first 650 meters. Then they broke through at the end of in the ventilation shaft. You see that on the right picture in the bottom. The 17.6 meter machine broke through, was decreased to 14 meters in diameter, and the parallel 14 meter machine just continued its operation through the ventilation shaft. The tunnel lining consisted of reinforced concrete elements. For the 14-meter mix shield, they used a total of 9 elements, 9 rings per ring, each having a weight of 14 tons. And for the 17.6 meters, a number of 12 elements were used with a weight of 12 tons per segment. But what I also want to highlight here in that project, because it was the first application of a new technology, was that for the 4.2 kilometers, you have to build also cross passages between the 2 parallel tunnel tubes. In total, a number of 44 cross passages have to be built for that job. And normally in soft ground, it's realized using the freezing technology. But here it was for the first time 2 machines were used to excavate these cross passages under demanding conditions with high hydrostatic pressures of up to 5.5 bar. These are small microtunneling machines, AVN machines, and they are installed on a trailer and start from one tunnel tube towards the parallel tunnel tube. They're pushed, it's a pipe checking technology towards the parallel tube. The machine drives into a reception bell, and you see on the right picture there was a demand from the beginning on that half of the tunnel alignment is still free, so that you can keep up the logistics for the running of the parallel machine. You see here the illustration, that's the reception bell where the machines drove in. After the machine drove in, it was transported here on a trailer, was brought out of the tunnel, again back into the parallel tunnel tube to start for the next cross passages. In total, we delivered 2 machines just to proceed the construction of the cross passages, because they are under a quite tight time schedule. You see here also a view of here the launching situation in one tunnel tube where the machine was pushed towards the parallel tunnel tube. The excavation lengths for these cross passages had been in the range of 12 to 15 meters. And in total, in average, such a construction for cross passages takes in average around 22 days. And once they made it a bit faster, they could have the best performances to build one of the cross passages within 14 days only, which is quite a good performance under these complex conditions. To conclude my presentation about large to very large diameters, you see that this technology is also feasible and reliably valid for even large to very large diameters. There had been numerous projects realized in the past with large diameters, also under complex geological conditions, like you see here for the Bosporus crossing, which is to date one of the most challenging projects. And the realization of such project gives also trust for future projects, also trust to the public, but also to the politicians and to the decision makers. And what is always important is that you have a very good teamwork tunneling, like I mentioned already, that you have a good working together with owners, designers, contractors, and machine manufacturers. With this, I want to thank you for your attention.